This is Katie Bowman's AP problem number 14. We'll start by reading the question. So, account for each of the following observations about pairs of substances in your answers. Use appropriate principles of chemical bonding and or intermolecular forces in each part. Your answers must include references to both substances. So, for the first question, it asks, though NH3 and CH4 have similar molecular masses, NH3 has a much higher normal boiling point at negative 33 degrees Celsius than CH4 at negative 104 degrees Celsius. So the answer is N has a higher electronegativity, which gives it a higher boiling point compared to C, or carbon. Carbon's boiling point is lower, so it has a lower boiling point. And then part B, or F, or whatever, asks, at 25 degrees Celsius and 1 atm, ethane C2H6 is a gas, and hexane C6H4 is a liquid. So the answer is both C2H6 and C6H14 both have like London dispersion forces, but because C6H14 is bigger and has more electrons, it has a higher boiling point. Since like LDF is mostly like, it's one of the weaker ones, but when there's a lot of it, it becomes a lot stronger, and this has more carbons in it, so it's going to be a lot stronger. It has 4 more, and it has way more hydrogens, so it's going to be a lot bigger, which is going to give it a higher boiling point. And then for G, it says Si melts at a much higher temperature, 1,410 degrees Celsius, than Cl2, negative 101 degrees Celsius. So the answer, Si is bonded covalently, and Cl2 is a weak London dispersion force, so the energy needed to melt Si is much larger than Cl2. Covalent bonds are a lot stronger than the London dispersion. London dispersion is only strong when there's a lot of it, when it's a really big molecule, and this isn't really that big. So then the last part asks, MgO melts at a higher temperature, 2,852, than NaF, 993. And that's because they are both ionic compounds, but the charges are bigger in Mg2. It's +2 and -2, and NaF is +1, -1. So the force holding MgO together is stronger, so more energy is needed to break the bonds apart, or in this case, to get it to melt. All right, that's it.